Welcome to this module on balanced ventilation with heat and energy recovery for the 2018 Washington State Energy Code. To get us started, let's talk a little bit about Build Tight and Ventilate Right, which there is another module dedicated to the general concept. But let's just cover that again real briefly here on why we want to build tight. We've all heard this build tight, ventilate right, but do we have the approaches that we need that are cost competitive, that bring sales opportunities, that are beneficial to resiliency, comfort, and indoor environmental quality? In this session, we'll briefly cover why it's important to build tight and to use balanced ventilation in these tighter homes. But then we'll move on to the most common strategies for getting each component right. This includes strategies for various balanced ventilation approaches and some tips and tricks along the way to make it work. My name is Dan Wildenhouse, Technical Advisor and Industry Liaison for Better Built Northwest. And on this journey, we'll look to getting homes dialed in for our codes, our certification programs, and maybe most importantly, our home buyers' future experience. At this point, we're going to move on to various ventilation approaches, some basic guidance, and then we'll jump right in to balanced ventilation strategies. So with some mechanical ventilation considerations, we should probably start by saying, what is an ideal ventilation system, right? Well, the first thing is homeowners need to understand it. We're going to talk a little bit later about homeowner education, but that's going to be a critical component here. Second, and maybe even more important, is that homeowners use it. We don't want them turning it off because it makes the home uncomfortable, or maybe even because they don't understand what that switch on the wall does. And then finally, it would be great if we could do this without having to use too much energy. So we've got the Washington State Energy Code looking to gain efficiencies, but the mechanical code is asking us to make sure we ventilate. So if we can find a way to do the ventilation without too much of an energy penalty, it's a win-win for both sets of code. Moving past that very general earlier statement, we now want to actually think about this in the sense that ventilation is really putting the V back in HVAC. Whether HVAC to you means heating, venting, and cooling, as a friend of mine in Texas would say, or heating, ventilation, and air conditioning. In either way, we often have been thinking about heating and cooling as a primary role of HVAC. But let's put that V back in. There's a couple of different ways we can do it. We can think about exhaust ventilation. We can think about supply ventilation, and we can think about balanced ventilation. For today's session, we're really going to focus on the balanced ventilation, right? This is where we introduce and exhaust approximately an equal amount of fresh air and polluted air from the inside. The way this is typically described in code in the IRC and the IMC is that the exhaust and supply flows should be within 10% or 5 CFM of each other. So we're going to jump in now to really thinking through the balanced ventilation approach. When we think and talk about strategies used across the country to provide balanced ventilation, there's really almost everything can fit into 7 different categories. We can talk about integrating in with our furnace, meaning we use an exhaust fan or multiple fans to exhaust air out of the house, and then we supply the same amount of air in, and we pipe that into our central air handler, and we try to make sure that those are balanced flows. We can do that continuously, which is option number 1, or we can do it intermittently, which is option number 2. In that case, we may use a tool called a fan cycler, a type of controller that prioritizes opening the damper for ventilation when there's a call for heating or cooling. And so this can actually have a little bit of energy savings because you are not, and potentially comfort benefit, because you're not always constantly blowing in untempered outdoor air. We can talk about using 2 fans, an exhaust fan somewhere and a separate supply fan, which is fairly easy to get balanced, but now you're not tempering that outdoor air at all. We could use a blended supply air box. So we actually attach a mixing box to our supply air fan and make sure that we pull some air from inside the house, some air from outside of the house, and then exhaust the same amount that we were bringing in from outside. This is a bit more of a complicated strategy. It works sometimes okay in retrofit strategies or major remodels where there's not a central air handler and the homeowner or the builder has not wanted to make the choice to go to a full HRV. But we're really going to talk about these next three. There's standalone energy recovery ventilators. We are only going to touch on these a bit today because for code's sake, these actually are very low flow and it may take 2 or 3 or 4 of them to actually meet the ventilation requirements for most homes. But effectively, these are a single unit, pipes air in and out, and then blows air in directly and takes air out of a central location or a single spot in the home. So it's not going to do much for distribution for you, but it can be balanced. We're really going to talk about standalone heat recovery ventilators and furnace integrated heat recovery ventilators moving forward. With these spot energy recovery ventilators, it's pretty a tempting approach, right? Because a company like Panasonic makes some of these, what they refer to as spot ERVs, and they're relatively inexpensive for a single unit. The challenge is, again, as I just mentioned, to provide balanced ventilation, these devices are only capable of being balanced up to 20 cubic feet per minute. We're going to talk a little bit later about the actual ventilation needs of the home, or you can review the Build Type Ventilate Right module, which actually goes into much more detail on that. But suffice to say, most standard mid-sized homes, 2,000 to 3,000 square foot homes, would need 2 or 3 of these devices to be put in. So while it is tempting because they're not incredibly expensive individually and can be fairly easy to install, you may need multiples of them. Also, again, as I mentioned previously, these are not truly distributed, so they're not really able to move air into all the bedrooms in the main body because, as is indicated, they are a spot system. So for the Washington State Energy Code, where there's a ventilation adjustment required if you're not balanced and distributed, you would actually need even more air. So again, 2 or 3 or 4 of these devices may actually be required if you're choosing this methodology. Next up, we have the standalone HRV, or the dedicated heat recovery ventilator. Now, to many people, this is what we think of, again, when we hear the words balanced ventilation. And the use of heat recovery or energy recovery is a pretty decent option because now, again, we're doing this without taking that big energy penalty. With these systems, the incoming air has a percentage of the outgoing air's heat recovered and transferred to it. So this might mean when we're exhausting 70-degree air and bringing in 30-degree air, we might be able to get that incoming temperature at least up to the low 60s, which is a whole lot better than 30-degree, 40-degree, or even 50-degree air blowing on grandma's head. One option with these is to exhaust out from the bathrooms. That's actually our preferred option. This often has very warm air, especially during shower and bath time, which can help treat both the indoor air quality of the home by removing it, as well as, potentially meaning that we could use a slightly smaller dedicated local exhaust fan in each bathroom to meet our International Mechanical Code requirements. We'll go into that a little bit more detail down the road here. We also really like that the new air coming into the home can be delivered into as many rooms as you care to duct it to, reducing the risk of bad indoor air quality throughout the home. This is an alternative visual, and if you don't already use the ASHRAE 62.2 users manuals, they've made them for the 2010 and for 2019. I recommend the 2019 user manual. It's very good, and what this is just showing you is the general layout of how this system would be set up. As you can see, if you follow the little blue arrows, you can see where air is being pulled from and where air is being delivered to in a home. And this, again, really gets us that ability to be both balanced and distributed. Again, with this strategy, there are both benefits and challenges. And in this case, we've actually added some where the best applications of this may be. So some of the benefits, again, it's both balanced and distributed air. You may be able to save energy on the home if you're using a high quality HRV with a good efficiency and a good efficacy. Don't worry, we'll cover those terms a little bit later. And you can pull exhaust air from the bathrooms and other high moisture air or pollutant areas. Again, hopefully benefiting your general indoor environmental quality and maybe reducing the size of the spot or local exhaust fans that are necessary. Challenges, of course, there's an increased cost compared to code minimum requirements. It does require ducting independent of other systems throughout the house. You need to deliver fresh air into both the main body and the bedrooms to really be distributed. And the system does need to be commissioned and balanced. Well, all of them technically do according to the code, but these can be a little challenging depending on the brand and the location of the equipment. And the location of the HRV itself needs to be in a place where basic maintenance can be done, particular access to filters. Now, this is generally a really good strategy for homes that use something like ductless heat pumps or radiantly heated homes or any type of heating and cooling system that is not inherently central and already distributed. If you have enough space, you can also put this in with a home with a central air handler, like a furnace or central heat pump. You're just running twice as much ductwork. So maybe you're saying, well, I don't want to run twice as much ductwork because I do have a central air handler. Again, maybe I have a gas furnace with an air conditioner, or maybe I have a central heat pump. Well, there is an option to integrate a heat recovery ventilator into that central air handler. And this sometimes combines both the best and the most challenging components of the other options. So in this case, the HRV or ERV is going to be ducted directly into the central ducting system for your central air handler. So this might reduce the amount of new ductwork needed and should ensure great distribution, right? Because your central air handler is already moving air to all the rooms. However, it also means that we may be relying on the air handler fan to move the air around, which is a lot higher energy draw than just using the fans included in the heat recovery ventilator. This integration will likely work best when connected to the supply side of your central distribution system, which may sound counterintuitive. We'll go into that more later. And we do this with an injection method connecting the ducts, not just with a saddle tee or a takeoff. Connecting to the return side can be done, but may require things like constant airflow regulators, different strategies for where you put your filters, and maybe even larger size return ducts. And this might be necessary to prevent hyperventilating your heat recovery ventilator. As you can see, there also can be some nuanced duct work that needs to happen with this type of integration. Our team has actually done some experimenting to make sure that this integration into the supply side will actually work. So you can kind of see this supply insertion in a demonstration product that we built. What ends up happening is, much like a rock in a river, there's a little kind of safe space, right? The eddies and whirls in the river that go around the rock create a little pocket of less turbulence. And that's what happens when this elbow or injection port is put into the central air handler. This allows our fresh air from our heat recovery ventilator to blend and mix quite well into a little pocket of less turbulent air. And then the entire system will pick that up and deliver it throughout the house. Again, we have both challenges and benefits, right? So the benefits we've already basically covered. It's balanced, it's distributed. You can select a variety of different heat recovery ventilators. You may even have multiple ways to do filtration, both filtration in the HRV and filtration in the home. So in wildfire areas, you might have double the benefit. But there are also some challenges to this system. Of course, it costs more than the code minimum, and it does require still running the exhaust ducting independent of the other systems. We're saying that half of the system should still be ducted independently. And this is where it gets really challenging. System commissioning and balancing when you're integrating into a central air handler can be pretty challenging. You need to have a good order of operations for how you commission the entire HVAC system, including the heat recovery ventilator. And it's going to be really critical and can be a little challenging. So there's a bit of a learning curve for this strategy for most builders and HVAC trades. And of course, we still have that same challenge of where do we put the heat recovery ventilator to make sure we have access to the filter and maintenance. So this is a pretty good application when you have a fairly tight home that already has a central air handler. And it's best to make sure that you size and control to run the HRV continuously, regardless of how often the air handler fan moves. So again, some challenges and some good applications for this strategy. It's still maybe not our preferred. Our preferred is still the fully distributed standalone HRV, but we do recognize that as you're bringing this into your work maybe newly, this may be a more enticing approach. So we want to make sure we cover it. We're going to go into greater details in some steps for success in just a few minutes, and we'll look at each of these in more detail. This has been a really great adventure with multiple different teams, green building certification programs, above code utility programs, and energy code support teams, all working together to come up with the 10 steps to success for using balanced ventilation with heat or energy recovery. So we're going to jump right in now. Okay, I know that 10 steps may seem like a lot, but some of these are short and easy, and at least one of them, there's an either or option here. So we're breaking basically this process down into small bites that you can think about and work with your trades on one at a time. So one of the first steps that we want to do is actually calculate the required airflow for the home. And I'm going to show you some math here. Don't worry, we're also going to show you a little bit later in our compliance section a great tool that you can use to help make sure that this is pretty easy for you. But let's talk through the math real quick. How much ventilation do we need in Washington State's energy and mechanical codes? So we need 7.5 cubic feet per minute per person, plus 1% of the floor area. That's the minimum. Tighter homes, if you start taking some of those energy credits from table 406.3 for tighter construction, you may benefit from putting in even more ventilation than the minimum. The tighter the home, the better it benefits with more ventilation, particularly when it's balanced. So let's do a quick example here. Let's take a 2,500 square foot home with 3 bedrooms. So 2,500 times 1%, that's 25 CFM. 3 bedrooms means 4 people in the way that math is done in the International Mechanical Code. So 4 humans times 7.5 is 30. And that means we need a total of 55 cubic feet per minute if we were to ventilate continuously. Now, because this is balanced ventilation and it's distributed, we don't have to do any multipliers towards this. And if we keep it continuous, we remove even an additional layer of multipliers. So putting in a heat recovery ventilator or energy recovery ventilator set to run continuously is probably the lowest total amount of ventilation that is required by code to be put in. Again, there's nothing wrong with putting in more ventilation, particularly with heat recovery. There's not a lot of energy penalty to it, and it's really actually probably a benefit, again, in tighter homes. Now, what if you don't want to run your balanced and distributed system continuously? What if you say, I don't like having to have this thing constantly running. Homeowners may ask too many questions. Well, one thing you can do is, this goes to the education of homeowners, and creation of a homeowner operation manual can help you there. But if you're committed to an intermittent operation, there are also coefficients that you must use to multiply. So let's take a look here. Most of our HRVs are recommended to run 24/7. But if we're choosing not to do that, then we need to make these adjustments. It also may change what HRV we're able to select based off of these volume changes. So choose the unit that's based on medium speed to meet your airflow is ideal for continuous, but you may need to meet based on a medium high or high fan speed if you're going to do intermittent ventilation. Okay, so in this example, if we were going to run our HRV for 20 minutes out of every hour, then we would need to multiply that total by 3, right? Remember, 55 CFM was our minimum requirement. Now, all of a sudden, multiply that by 3, that's 165 CFM. That is a much larger heat recovery ventilator that you need to purchase to be able to do this work. What if you decided to run it 40 minutes out of every hour? You still need to multiply it by 1.5. Now, that is, again, a big change. So we really are thinking with heat recovery and energy recovery ventilators, whether they're spot, standalone, or integrated, running them continuously is the best way to ensure that you can get a small or have a flexible number of HRVs to choose from, which can help you reduce cost, make it easier to install, and maybe even cut down noise when they're running, because a 55 CFM continuous heat recovery ventilator is likely to be a little bit more quiet than a 165 CFM unit that is running intermittently. Up until this point, we've been showing you the math just kind of on the paperwork. And we recognize that for some folks, that feels like, okay, this is a lot of mental gymnastics and a lot of paperwork. Well, there's some good news. There are some good ventilation airflow calculators out on the market. There are some that you can Google and find online, but Washington State University Energy Code program actually has developed a code compliance calculator that has a section specifically on ventilation requirements. It does a lot more than that, and there are some other training modules and some videos that show you how to use the code compliance calculator. But in a little bit, we're actually going to do a demo of how to use it specifically for the ventilation requirements. The next step in choosing a balanced ventilation strategy is going ahead and making the decision to go with energy recovery or heat recovery. We've said these terms a couple of different times, but we haven't really gone into that yet. So let's talk a little bit more about what the difference is between these two. A heat recovery ventilator, or HRV, transfers what is referred to as sensible heat, or just temperature, between the two airstreams. So the air being exhausted out and the air being supplied in, they go through a core. The two airstreams don't actually touch. They go through a heat exchanger and allows some of that heat to be transferred to the incoming air. A condensate line, because condensation is likely to happen in a scenario like this, is involved, and it needs to be run to a trapped drain. An energy recovery ventilator, on the other hand, transfers that sensible heat, or the temperature, plus what we call latent heat, or enthalpy. It's another way of saying the energy that is also involved in moisture movement. So latent heat really is the energy value of water vapor in the air. One of the benefits of an energy recovery ventilator is you don't need a condensate drain. And they do tend to have a slightly higher overall efficiency. If there's a challenge to ERVs, it's that they may cost a little bit more. Depending on the brand, some of them, the cost is very, very similar between their HRV and their ERV. Others, the cost is higher for the ERV. Next, we talked about the balance or standalone, or dedicated HRV. Again, this one uses its own set of ductwork, regardless of ductwork that you may be using for a central system. So it does have additional considerations. And then there was the integrated heat recovery. And again, we will go into more details on the ducting and specific about this a little bit later. We're on to step 3, selecting efficient equipment. First things first is there's some good news. The Home Ventilating Institute, or HVI, has an entire certified products directory. Now, not everything that is colloquially referred to as an HRV or ERV is going to be in here. There are a few manufacturers who the process that they use does not align with HVI testing. But for the most part, the majority of the market is going to be located in the HVI directory. So it's a great place you can go. Some considerations here. We want to size an HRV, specifically if we're thinking for continuous ventilation, to deliver the airflow at its medium speed. I'll show you in a minute how you can look that up. We can use measurements at 0.4 inches of water column. So essentially, we want to make sure that ducting has been done right on this so that that airflow selection makes sense. We do want to look at our energy fan consumption. That's also referred to as the airflow efficacy. And what we want to go is to get 1.25 cubic feet per minute for every watt of fan energy that we move. This helps make sure that the fan running constantly is not wasting a bunch of additional electricity. as we've gone through all of these efforts to make our home more efficient. We want to run many hours of air continuously is ideal, again, to keep us from having to supersize our heat recovery ventilators. We want to make sure that the equipment that we choose use electrically commutated motors, or ECMs. They're much more efficient, may allow for variable speed. And then finally, while yes, there is a level in both the Oregon and Washington codes that allow for a 0.65 or 0.66 SRA piece of equipment, we really, if you want to maximize that tempering of incoming air and get the best overall efficiency, we really want to look at sensible recovery efficiency, or SRE, of 75% or higher. Again, you can find all this on hvi.org. Now, you can make an argument that step 4, determining the control strategy, could actually be step 3. It's a little bit interchangeable here, because here we're really talking about making the decision of whether or not we want to do continuous operation, which allows us, to use medium speed and then have a high speed boost as needed. To think about, do we want to do this as intermittent, and do we have the ability to displace some of our local exhaust? By displace local exhaust, I think we're going to talk a little bit more about that a little bit later, but effectively, if you're constantly removing, let's say, 15 CFM out of a bathroom, the Washington State Mechanical Code is going to have a prescriptive number that you need to meet for what they refer to as local exhaust. So you could subtract 15 CFM off of that number, and that typically means you can get a slightly smaller fan installed. So instead of having to buy a 90 CFM local exhaust fan, you could potentially buy a 70 CFM. So there may be a little bit of cost savings there by combining the continuous ventilation from the heat recovery ventilator, that continuous exhaust, with the on-demand local exhaust, so that at any point in time, you're either constantly moving a small amount of air, or when combining the two, are taking care of any local instances, creating of moisture or pollutants, and removing them effectively at that time. Next up, step 5, we want to locate all of our interior exhaust points. So where are we going to pull air out of the house? So this is pretty great, because obviously we want to remove pollutants in the places that they're caused. So we want to remove humid and odoriferous air, meaning stinky, smelly air, out of the house. The HRV may be able to displace some of the bathroom fans again. We do not recommend combining this with your kitchen range hood. We really want you to focus on bathrooms and utility rooms. Now, to that displacement, the question here, will the HRV replace the bathroom fans? It's a little bit more complicated than that. On the one hand, if you were to try to replace it entirely, the mechanical code does allow for a small continuous ventilation rate to satisfy the local exhaust requirement. But one of the problems with that is homeowners don't like fogging mirrors, right? And if you're trying to clear out the moisture in a bathroom after someone takes a shower, it takes a lot longer to defog that mirror with a low flow rate than it does to have a higher flow rate for a shorter amount of time. So we want to think about that. But again, I keep using this word displace, right? So in this case, if we want to move, say 10 or 15 CFM out of that bathroom more or less continuously, and by the way, there are some things like defrost cycles that have to happen with pieces of equipment where they temporarily maybe only recirculate air, so that's another consideration. But we can take a look and say the best case scenario might be we could put in a 70 CFM bathroom fan instead of a higher one. And that's going to meet 88% of the local exhaust requirement all by itself. And then the HRV exhaust will do the rest. So this may still have some builders, some savings, because you don't always need an 80, 90, or 100 CFM local exhaust fan. If you can get away with the 70 plus a small amount of continuous ventilation exhaust from your HRV, you're pretty well set up for success. Again, we cannot emphasize this enough. We really want to pull the exhaust from the places where the contaminants are common, right? As opposed to connecting it to a central return duct. Why? We want to prevent pressures of the central duct system from overpowering our HRV. That can actually happen when you connect an exhaust to the return side. of your HRV, the pressure in the central air handler duct is much greater, a much larger number than is the pressure created by the heat recovery ventilator, so it can actually overpower the HRV. Heat recovery opportunities from our bathrooms are good. Steamy, moist, wet, warm air has a little bit more heat to transfer out of it typically, so that can improve our incoming airstream temperature. Right? This again offers that ability to offset the HRV costs by maybe even eliminating fans in half bathrooms and utility closets and reducing the size of fans necessary for those full bathrooms. And then, of course, opportunities to pull air from the high contaminant locations is always a good thing, right? All of the bathrooms, the utility rooms, the laundry rooms, those type of places, that's where we create pollutants on a very common level. Again, we're not really saying go to do this with the kitchen. We know that at some levels of efficiency, when you get down to the passive house level, this becomes a much more common approach. But for most of you builders out there, don't do it out of the kitchen. Go ahead and do it out of all the bathrooms, utility rooms, laundry rooms. Now we have to think about where are we going to supply the new air into the home. In particular, we're talking about standalone heat recovery ventilators. Integrated ones, of course, are supplying the air through the heating and cooling ducts in the home. So in a standalone HRV, we want to encourage as much mixing in the house as we possibly can. We'd like to get it into bedrooms, maybe even high up on the wall. And we want to avoid direct flow onto occupants. So, you know, grandma is sitting in a rocking chair, even if that incoming air temperature is in the 60s and not the 30s, it still may not feel comfortable to her. So one option that we've heard people thinking about is putting these into closets. And that can work, but if you put it into the closet, a couple of things need to happen. You don't want to put it directly over the shelves. You know that Aunt Sylvia is going to cram a bunch of hat boxes up there and is going to likely disturb that airflow. Also, if it's in a closet, it's ideal to have it right over the door where some of those openings are. And speaking of the door to the closet will need to either be undercut or probably louvered to get those best results. You don't want to just ventilate the closet. If you have a tight closing closet door, it doesn't really help you that much. Next up, let's locate our exterior supply and exhaust points. So we want to be thinking about both the incoming outside air as well as the outgoing inside air. Ideally, we want to maintain 6 to 10 feet between the two. This helps to make sure that the air that we just exhausted out of the house doesn't get sucked right back in. That doesn't do us too many favors for our indoor environmental quality. Second, we want to avoid areas where there's likely poor outdoor air quality. So at the driveway, particularly in colder climates where people idle their cars and trucks before driving to work in the morning. Up on the roof, not only is it very difficult to get up there to ever do any maintenance, you know, asphalt shingles can be hot and stinky. Birds may want to nest in it. Putting it up high on the roof is usually not a good idea. And then right next to where the dog house is, where the barbecue is going to be, the hot tub, anything like that is a local, you know, ideal that's probably not going to work for you. You don't want to be sucking in that type of air and distributing throughout the house. And finally, again, we're going to talk later about maintenance and homeowner operation. Make sure this is accessible for cleaning, especially the intake. You know, you've got a mesh screen on there. Over time, new outdoor air being sucked in over and over and over with pollen and dirt and animal hair, all those things, it will eventually get clogged. So a basic piece of maintenance is being able to get access to it. So again, as I said, roofs are not a good idea. 12 feet off the ground is probably not a good idea. If you can think about it, 2 to 5 feet off the ground in a good location, that's ideal. On to step 8. Where do we want to locate the actual fan unit itself, the heat recovery or energy recovery ventilator? Ideally, a central location is great because that may minimize the amount of extra ducting that you need to do. If you're using a heat recovery ventilator, you do need to think about where that condensate drain is going to go. You want to think about noise, probably not in the master bedroom closet, for instance. Again, any opportunity to minimize our duct length will be a good thing for our static pressures. It helps make sure we get the flow we want. We want to make sure we can facilitate getting all of our ductwork inside of our thermal envelope, meaning inside of the insulation and air barrier of the home. We want to make sure that you put it in a place where you can actually take advantage of this as a sales feature. We've had some builders be able to actually show to homeowners, this is the lungs of your home, and we decide that for your efficient home, you should have an efficient ventilation system. It's right here, and it becomes an actual sales feature, something that the sales agents can actually sell. Some of the really good options for places to put this, a utility room, maybe above that washer and dryer, a hallway closet, or if you've moved your air handler and all your ductwork inside, then in the utility closet that is hosting that might be a good place. Again, think of all of these things simultaneously when you're citing this, and make sure this gets into scopes of work and details get into plans. So far, most of the steps we've talked about make a lot of sense and have been relatively simple. Now we get in where it's a little bit more complicated and challenging. So these components are where you really need to engage with the trades that will be involved in installation. So creating a dedicated duct system, if you're doing a standalone HRV, is your next big step here. So again, these are really good for houses with ductless heat pumps or radiant heating and cooling systems. Ducts are ideal if they're short, straight, and smooth. We don't want a bunch of 90-degree elbows. If you use flex duct, try to limit how much you use or make sure that it's been pulled tight and straight. You want to make sure that you seal all the ducts and the fittings with mastic paste, not just duct tape. Duct tape is great for just about everything in the universe except duct work. Again, ducts should be inside the conditioned space or very, very well insulated. And we want to insulate all ducts running to outside ports, and we want to be considerate of the fact we may need balancing dampers if the manufacturer recommends it. This gets to be very interesting, and it's where you want to have really good conversations with your HVAC trade and the distributor, because some brands have balancing dampers built into the heat recovery ventilator, others do not. If it does not, you may need to install them into your ductwork so that you can decide which ones to kind of open a little bit more and shut a little bit more, so you can actually, again, distribute the air where you need to fairly evenly throughout the home, and pull air where you want to fairly evenly throughout the home. I know some of you are thinking, but Dan, I really wanted to hear more about how we could integrate our heat recovery ventilator into our central air handler. We always put in gas furnaces or electric heat pumps in our homes. We want to take advantage of that. So we can do that. The best approach for doing something like this is, first of all, let's be realistic about how much airflow is being moved. That central air handler running at full speed is likely moving anywhere from 1,000 to 1,600 cubic feet per minute, whereas an HRV might be moving anywhere from 50 to 250 CFM. Very different orders of magnitude. So because of that, we want to make sure that let's say 200 CFM of HRV air actually blends very well into that larger airstream. So the best approach to do this, we call it a partially ducted system. We fully duct all of the exhaust out of all the bathrooms, utility rooms, laundry rooms that we talked about earlier. But then we take the HRV supply and we connect it to the forced air central system's supply duct. And in just a second, we're going to go into a little bit more detail on this. Okay, Dan, so tell me what really, really well means, right? Maybe this is just really my only option. If you look at the lower right-hand corner of the screen, you can see the ducting is going into the return side. So if you're going to do that, we want you to think of a couple of things. Don't install filter grills in the home, right? This is nice because filter grills, people tend to like them because homeowners can actually see the filter grill and they know to change out the filter. But part of the problem with that is as the filter, the dirtier it gets, the more static pressure builds up in that return duct. And remember that higher negative static pressure, or the more negative static pressure in that return duct, the more it's sucking on that supply duct from the HRV. So that can be a challenge. So If you can help it, don't install filter grills if you are going to integrate your HRV into the return side. Second, you can use a product called a constant airflow regulator. If you look at the upper right-hand corner, those are CARs, or constant airflow regulators. And there's a couple of different models and brands out there. This one uses a bladder that actually inflates as pressure builds up around it. So the velocity of air starts going through faster. It creates pressure. That little bladder in there inflates a little bit. And what a constant airflow regulator will do is kind of insist that you don't go beyond a maximum amount of flow. There are other types which are kind of gravity dampers that work similarly. Constant airflow regulator is a pretty good way to make sure that the lower the pressure, the easier it is for air to move through it. But when you get a high negative pressure in that return, it will not oversuck more than the designed amount. And finally, you should be doing manual J, D, S, and T for your central systems. You might want to oversize the return duct portion of your central air handler. It's almost never a bad idea to do that, but particularly when you're doing this. Again, if you have a slightly larger return duct component of your central air handler, the negative pressures inside of it will be lower because the same volume of air, but through a larger duct means a lower pressure or a less negative pressure. You combine all three of these practices and you could actually connect to the return side without too much of a penalty. The final required step to doing this is the testing and commissioning of these systems. This is required by code. Some jurisdictions may even mandate that a third party do this. So in other words, not the installing contractor. So be very aware of what your local jurisdiction requires, but this is required by code. You need to make sure that the system is balanced to its manufacturer's specifications. You measure the airflow at all the exhaust and supply points and then make some adjustments as necessary. There's a standard out there called ANSI ResNet 380 2019. And this provides some really good guidance on commissioning protocols. So if you're looking for a way to say, I'm not sure how I'm supposed to be doing all of this, start there and always rely on the manufacturer's recommendation. They will always give you good guidance as well. On top of all this, we also need to educate the occupant. The occupant needs to understand how the system is designed to operate. They need to know what maintenance will be required, and it's ideal if they have a set of written instructions or a short video available. Think not just about the first homeowner, but if the average amount of time people spend in a home is 7 years, and a heat recovery ventilator is designed to last 25 or 30 years, then there could be a second or third homeowner down the road who also needs this information. So it goes beyond just explaining to them in person. Giving them a written set of instructions or digital way to understand to do this, such as a short video, is really ideal. So testing, commissioning, leading towards homeowner education, required by code, and this is maybe the most challenging part that we've seen people be able to do repeatedly. The more often you do this, the easier it will become. I mentioned very early on in this module that the worst ventilation system is the one that is not turned on. And that is often because the homeowner doesn't understand. So one simple technique is to make sure you're doing proper labeling of the systems for the homeowners. In fact, there's actually a checkbox, and we'll get to this in a little bit on compliance, of did you label the ventilation system for the homeowner so they understand. The good news is you don't have to create your own labels. There's several out there in the marketplace. On the left-hand side of the screen, Lawrence Berkeley National Labs has these great equipment labels. You can pick and choose the one that works for you. On the right, HVI, the Home Ventilating Institute, also has some installer guidance, which includes the ability to print these stickers. These are all really good first steps to making sure the homeowners do not accidentally turn off their ventilation system. Of course, education needs to go beyond just making sure the homeowner knows they have a ventilation system. So we highly recommend actually developing guides for just the critical and technical components of the home. So here we have a heat recovery ventilation guide for houses as an example, which shows the different modes of operation and provides some maintenance information for homeowners. But you could also do an overall home operation manual. It's kind of crazy. I can buy a Blu-ray player. Yeah, they still sell those. I could buy a Blu-ray player for $80, and it's going to come with a 90-page manual in 2 or 3 languages. And yet I can spend $200, $300, $400, $500, $600, $700,000 on a home, probably the largest purchase I'll ever make, and it doesn't come with an operational manual. It seems like a disconnect to me. So let's correct that. It's worth investing in homeowner operation manuals. It will do nothing but help your homeowner understand how to operate their home. And homeowner referrals is one of the best ways to stay in business. So let's wrap this up with just a few resources for you. As we wind this up today, we want to show you a couple of really great resources. There's actually a ton out there. We'll give you my contact information included, but start here. The WSU Energy Program website. This is where you're going to get the most robust current set of all the tools you need to help you be able to meet the residential portions of the Washington State Energy Code and the Washington State's version of the International Mechanical Code. Next is Better Built Northwest, and this website is a great location. It has more detailed trainings. I shouldn't say more detailed, more in-depth trainings that go above and beyond code. This is really a location to culminate all of the effort in the Northwest to build homes better than code. And then finally, the Building America Solution Center. Effectively, every piece of research that's been done over the past 20 years with the DOE's Building America program lives on this website, and there are a ton of great resources, everything from code briefs to program checklists, how to think about different building components, program checklist or disaster resistance, and a sales tool for your sales staff to help them learn how to take some of these code requirements and turn them into something that can be a sales advantage for your team. And there's actually continuing and ongoing training available. So we've put together an online training platform. You do have to log into it, this learning management system, but the benefit of doing that is there may be continuing education units available for you. So if you need AIA credits, or if you are a commissioner and you need ResNet professional development hours or Building Performance Institute CEUs, by logging into the LMS, you can get the full versions of all of our trainings for free, and you can get registered for continuing education units. We also are putting some shortened versions and some other content on our YouTube page. These are typically all an hour or less. Target for a lot of these is around 45 minutes, but great ways to learn even more. And there's probably going to be additional links to these YouTube pages from a variety of other websites. So there's a lot available on demand at your fingertips as you want it. And with that, I am and have been Dan Wildenhouse, and it's been a pleasure to walk through this with you. If you have questions or concerns after watching this video and you'd like to know more, please reach out to me. My email address is right there, dwildenhouse@trccompanies.com. Go ahead and email me and I'll be sure to respond to you. And thank you so much for your time today. We respect the fact that time is valuable and it's a resource, and you've just given some of yours to us, and we're grateful for that. I hope it's been a benefit to you.